So um welcome everyone. Today we have Minxin Zhang from UCLA to give us a talk. So Minxin is currently a Hedrick assistant adjunct professor, and she got her PhD from University of San Diego. And
No,
yeah,
University of California, San Diego.
yes. And I do want to advertise Minxin is on job market this year.
Yes,
Yeah,
very
yeah, so
perfect.
please take away. Yeah.
Okay, thank you. Thank the organizer for organizing this, and thanks team for inviting me. So today I'm going to tell you some recent advances on structure-aware adaptive non-convex optimization for applications in deep learning and scientific computing. So as we all know, non-convex optimization is the cornerstone of deep learning and scientific computing. So in the pictures here, I'm showing you two examples. On the left one is the like Meta's large language model lemma. Right? If you want to train this large language model, both the model size and the number of tokens is at the scale like billions, which is the scale that people don't really encounter before the age of AI. And in the picture on the right side, it's a DNA training model. So in many scientific research in biology or chemistry, a very important promise to how to do the minimization of the energy configuration on this DNA chain model. So for a very simple case, even in a very abstract and simple case, say if you consider 15 pairs of 15 80 pairs on that DNA chain, and each AT pair has its own energy function. And if each energy function is like a double well function with two local minimizers, and if you add 15 of them up, then you end up with a total energy function, which has like a 2 to the 15, 2 to the power 15 number of local minimizers. So how do we escape all those huge number of local minimizers to eventually converge to the global minimizer, this is a challenging problem. So overall, advances in AI and science pose optimization challenges of unprecedented scale and complexity, calling for fundamental advances in non-convex optimization. So today, my talk will present two of our recent advances in non-convex optimization based on two motivations. So one is that recent evidence is showing that for large-scale training deep learning, exploiting metric structures of neural networks can enhance training efficiency. So we propose a new optimizer. We name it as AdaGO, integrating adaptivity with matrix-aware optimization. And second one is that for many scientific applications, especially when gradients are unavailable, either it's very expensive to compute or it's just not computable, then common global optimization methods such as simulated annealing, particle swarm optimization often lack convergence guarantees and suffer from curse of dimensionality. So we propose a new class of algorithm. We call it inexact proximal point algorithm or IPP algorithms, incorporating adaptive sampling and low-rank tensor approximation to achieve both the scalability and the practical efficiency. So here's the outline of my talk. The first part, I'll tell you about our new optimizer AdaGO for deep learning. The second part, I'll tell you our IPP algorithms for zeroth-order global optimization. And then I'll conclude and tell you some future directions. So first part, title is AdaGrad meets Muon, adaptive stepsizes for orthogonal updates. This is joint work with Yu Xuan, who is a PhD student at UCLA, and Professor Hayden Schaefer, also at UCLA. So the background is that earlier last year, there's this new optimizer called Muon optimizer is proposed, and there has been increasing evidence demonstrate that the superior empirical performance of this optimizer is especially in large language model training. So if people are familiar with like a stochastic gradient descent, like SGD, then here's the some like overview of this algorithm. So basically, it's summing up sample a mini batch of size a certain size and compute that stochastic gradient, and then it accumulates a momentum. A standard SGD would use this momentum to update these trainable parameters in neural networks, which are usually matrices like weight matrices. What's different in this new Muon optimizer is that instead of directly using MT, the momentum, it uses this so-called Newton-Schultz algorithm to approximately also orthogonalize this momentum matrix, and you get OT, and then use OT to update your weight matrices. So based on this empirical evidence that's saying that orthogonalization is beneficial. But why is that? There are many recent papers like analyzing and discussing it. But here we consider the very simple case when there's no momentum and no noise. And I want to emphasize two key facts about this orthogonalization. So comparing to like standard gradient descent, so if your standard gradient descent uses this gradient matrix GT, and if this GT has a reduced SVD decomposition, UT sigma T times VT transpose, then the orthogonalization of this gradient matrix is simply U times V transpose. And why is this orthogonalization a good choice? There's one way to interpret it is that standard gradient descent is the steepest descent direction, but under the standard Euclidean norm. And for orthogonalized gradient descent, it's also a steepest descent direction, but under the spectral norm. So if you think about the neural network structure, it's the weight matrices acts as operators on the hidden neurons. So spectral norm also has another name called operator norm. Based on this intuition that the weight matrices act as operators, so we can expect that the spectral norm is a better choice than Euclidean norm especially in training. So empirically and also theoretically, Moore's orthogonalized updates significantly alter the optimization dynamics. So two key components in an optimization algorithm is that you want to have a good like update direction, search direction. In this case, Moore is proposing an orthogonalized update direction, but another key component in optimization is the learning rate or the step size. So once we determine this direction, how far we want to go along this direction at each iteration. So Moore proposed this good update direction, which makes a reconsideration of the other key component, which is the learning rate selection, to be important. So this is a question that we want to address in our work. And here are two motivating examples. So just to consider a simple case when you want to train one linear layer. And if you use a standard gradient descent, you get this blue curve here. And if you use orthogonalized gradient descent, if you use together with a small constant learning rate, like in this orange line here, then you can see the convergence rate. The convergence speed is actually not faster. It's actually slower than the standard gradient descent. But if you use a much larger constant learning rate, like this red curve here, then it has a very rapid drop initially in its training loss, but it ends up with plateauing and oscillations. And the similar phenomena are also observed in nonlinear case, like on the picture on the right-hand side, we train like one attention layer. And you see that if you use a small constant learning rate, you get this orange curve, which decreases more slowly initially, but eventually it gets a smaller final training loss. Whereas if you use a larger learning rate, like in this green curve here, it drops initially like more rapidly, but it ends up with plateauing. So based on these two observations, we conclude that if we could propose not a constantly rate but an adaptive learning rate schedule that is informed by especially past gradient information that has the potential to further improve the efficiency of the current Muon optimizer. So what kind of adaptive step size we want for this Muon optimizer? We consider a common type of adaptive step size called AdaGrad, which was initially proposed in this paper around 2011 for stochastic optimization in machine learning. And the idea is basically that you have a number of past gradients like this GTOL, you accumulate it and you get a gradient, at least accumulating matrix GT. And then at each iteration, instead of directly using the standard like a standard stochastic gradient, you use this GT matrix to scale this, and then use this scale direction to update the weight matrices. And this has been shown to be effective, especially when your gradients are sparse. But this is also more like computationally expensive because it involves computation of the inverse of this matrix. And later in 2020, there's this paper proposed this AdaGrad norm step sizes. So instead of accumulate the gradient and formulate as a matrix, it only accumulates the norms of the past gradients and then use this scalar, scale this stochastic gradient, use this scalar. And there has been many theoretical analysis about this AdaGrad norm as well as experiments. And mainly this type of AdaGrad norm step size is able to adapt to noise levels and also automatically adapt to the smoothness of the objective function. So in our case, we want to propose adaptive step sizes for the Muon optimizer. So we want to something like this AdaGrad norm instead of AdaGrad. There are two reasons. One is AdaGrad with the full matrix is more, oh sorry, it's more is more computationally expensive, and whereas AdaGrad norm only accumulates a scalar variable. And the other reason is that because we based on the evidence from Muon optimizer, the orthogonalized update directions are beneficial, right? But if you use another matrix like GT to rescale that orthogonalized update direction, then that orthogonality would be destroyed, which would basically destroy the advantage that the orthogonalization has brought to this training. Instead, for AdaGrad norm, you can simply use a scalar to scale that orthogonalized grid up direction, which preserve the structural advantage of that orthogonality while adapting scale this update direction. So based on the background in this Muon optimizer and also this AdaGrad norm, we propose a new algorithm. We call it AdaGO. So basically, we have evidence that showing that adaptively tuned learning rate schedule informed by past gradients has the potential to further accelerate and stabilize the Muon optimizer. So we ask the question, can we derive a type of step sizes like AdaGrad norm for this Muon optimizer? And after some theoretical analysis and experiments, we answer that yes, but it requires some modifications, mainly because this orthogonalization, if you think about it, it's actually an unbounded operator, right? It can potentially amplify the effect of noise in stochastic gradients. So we want some modifications for this AdaGrad norm to work for the orthogonalized update. The two main things is that we clamp gradient norms by some constant gamma to eliminate AdaGrad norms restricted assumption of bounded gradients. So in original analysis of this AdaGrad norm for standard SGD, then it imposes this assumption to make sure that it converges. For our algorithm, we just clamped gradient norm to remove this and empirically and also theoretically analyze that the performance of our algorithm remains robust across a wide range of different gamma values. And the second key feature about our new optimizer is that instead of naively accumulating gradient norms or decaying step sizes, we observed both empirically and theoretically that it can slow down convergence. Instead, we impose that lower bound, epsilon. This epsilon is usually dependent on t and needs to be tuned, but this ensures that it does not really slow down the convergence. So this is how our algorithm looks like. It's basically very similar to the original Muon optimizer, except that we scale our orthogonalized update using this scalar here. So it's a maximum between a small epsilon and this ratio. This ratio is it's likely AdaGrad norm, but we clamped this gradient norm with this gamma, and in the accumulation VT or the accumulator, we also accumulate like a clamped gradient norm, the score of clamped gradient norms. So this is our algorithm. How does this new algorithm work? One thing you can notice that because it only accumulates a scalar variable, right? So it almost does not add any additional computational cost comparing to the Muon optimizer. And then we also did a theoretical analysis on this new optimizer, and we established optimal theoretical convergence rates. So basically, we did that under very standard assumptions. One is that we assume that the gradient of our loss function is Lipschitz continuous with some Lipschitz constant error. And for the stochastic gradient, GT, we assume it's an unbiased estimate with uniformly bounded variance. And these are standard assumptions when it comes to optimization algorithms for machine learning. And then in our paper, we establish optimal convergence rate, which means that in the deterministic setting without momentum or noise, if we set this epsilon to be this magnitude and eta to be something that is smaller than 1, then for larger t, this algorithm, our algorithm converges to a stationary point at this rate. So basically, if t is large, it's like converging to the station point at a rate of big O of like 1 over square root of t. And in the stochastic setting with momentum, if we set our hyperparameters like this, then for large t, this algorithm converges to a stationary point with this rate. So basically, when t is large, then it's converted to a stationary point at a rate of big O of 1 over t to the power of 1/4. So as I said, these are optimal convergence rates, which means based on these theoretical results from these two papers, they are actually the best possible convergence rates we can obtain for first-order methods under the standard assumptions that I showed you earlier. And that's how the algorithm works in theoretically. Empirically, we are still investigating our algorithm, the behavior of our algorithm in training large language models. But here are some small scale experiments. So in these experiments, we did the function regression. Basically, we generate a data set by sampling 10,000 points from a Gaussian random field with 15-dimensional input and 15-dimensional output. And we use multi-layer perception to do the regression. And as you can see in the two pictures, that we compare our algorithm with the Adam, the widely used Adam or Adam W, and the Muon optimizer. And you can see that the green plot is the result of our algorithms. You can see that our algorithm is able to achieve is able to converge faster and achieves both the lower final chain loss as well as the better test accuracy. And the second experiment we did is to do CFI10 image classification. We use a convolutional network with three convolutional layers and two fully connected layers, and we train for 100 epochs. And you can see in the two pictures that both the training loss and test accuracy for our algorithm achieve the better performance comparing to the widely used Adam as well as the new optimized Muon. So this is the first part of my talk. Does the audience have any questions about this part? Okay, if not, I can continue to the second part, which is inexact proximal point algorithm for zeroth-order global optimization. This is joint work with Fuqun Han, who is a postdoc at UCLA, and Yating Chu, who is a professor at UC Riverside, and Professor Stanley Ocean and Henry Shiver at UCLA. So here's the problem we consider. We consider a very general, like global optimization problem. For using zeroth order means that we do not use any gradient information, but merely depends on function evaluations. And we impose very mild assumption, a very weak assumption. We just assume that its objective function is continuous and it can be non-convex. And we assume it has at least one global minimizer and possibly multiple local minimizers. And in the picture here is an example of the benchmark function in the global optimization research, which is called the gray function. And in this case, it's only a function of two variables, so it can be shown in this 3D picture here. As you can see, that this function has very complex landscape. It has so many local minimizers. So how do we get past from all these local min? We first establish a theoretical framework for our algorithm. So if people are familiar with optimization, then you know that the proximal operator is actually a very classical notion in optimization. The idea is that instead of directly minimize this complex function f, we add a quadratic regularization term to this function and solve it iteratively. So we are converting the one problem of minimizing the function f into minimize a sequence of quadratically regularized function. And so basically that if you start with an x0, then in the next step you compute the proximal operator at x1. Or start from xk, you compute xk plus 1 by compute this proximal operator, which means you want to minimize the quadratic regularized function. So for a non-convex function, and if the t, so this t is basically the weight coefficient on its quadratic regularization. And if this t is large, then evaluating the proximal operator itself is actually a very difficult non-convex global optimization problem, which is impractical to solve exactly. We introduce a class of inexact proximal point algorithm that iteratively evaluates this proximal operator inexactly. So here's the outline of this algorithm. Basically, is that at each iteration k, we compute an approximation of this proximal operator at the coordinate reach xk, we get an yk, and then we update our xk using this yk. And this alpha k is called a damping parameter, which is between 0 and 1, mainly to prevent the algorithm to iterate, to go to proceed too fast but along the wrong direction. So this alpha k is used to as a damping parameter. And then once we update this xk, to xk plus 1, we look at a quantity called qk. If qk is small, then we increase this tk to so if you look at if tk is increased, meaning that we put less weight on this quadratic regularization term, meaning that we are encouraging algorithm to do more like a global exploration. Whereas if qk is large, meaning that this next iterate is a bit far away from the current xk, then we reduce this tk to encourage more like local exploitation of the landscape. So this is the framework, and we have established theoretical convergence of this IPP method under very mild assumptions. One assumption is that f needs to be continuous and have at least one global minimizer x star, and f should be p-coercive, which basically means that when x goes to infinity, then the value of f of x should also go to infinity, which is a very mild assumption to ensure that the x star like resides in some bounded regions. And the last assumption is less common, but still it's a very mild assumption, which says that there should exist a positive mu such that if this x is the stationary point of f and the function value at x is less than the minimum of the f plus this small mu, then these two conditions together imply that x is actually the x star. So if you think about it, this assumption is merely to exclude all the cases when this function is like extremely oscillating around this x star, which rarely happens in practice. So under these three mild assumptions, we established in our paper, we established the theoretical convergence to converge that the algorithm converge to the global minimizer when either deterministic or stochastic estimates or proximal operators are used. I'm not going to tell you details about this analysis, but it can be found in our paper. And the main thing I want to say is that based on our analysis, is that the convergence of this algorithm relies on estimating the proximal operator with sufficient asymptotic accuracy. So now that we have this framework, and the next question is how do we turn this whole framework into a practically efficient algorithm? And as I said, the key component is to estimate this proximal operator efficiently and with sufficient accuracy. And for this purpose, we propose a new approach called tensor-train estimation of the proximal operator. We started with considering this Gibbs measure associated with this function phi. So phi, as I showed you in a previous slide, that phi is the quadratically regularized objective function f. So f is the original objective function, and phi is just f plus that quadratic regularization term. And as a classical result about this Gibbs measure is that if this proximal operator is single valued, and with a small positive delta, then the expectation of this Gibbs measure is approximates the Dirac measure centered at that proximal operator. So basically, if we have a good approximation of the expectation of this Gibbs measure, then we get a good approximation of this proximal operator. So to do that, the proximal operator can be estimated by simply sampling from its associated Gibbs measure. And so why do we want to look at to consider its Gibbs measure instead of like directly solving the proximal operator as an optimization problem? One reason is that if you consider some like a standardly used optimization algorithm like gradient descent, then it can easily stack at the local minimizer rather than global minimizer that we are looking for. And the other reason is illustrated in this picture here. It's because the landscape of this associated function actually allows like efficient sampling from this Gibbs measure. So here's an example is that we consider a two-dimensional benchmark function called the Sheffer function. which is showing in this picture A here. You can see it has very complex landscape with many local minimizers and maybe only one global minimizer. And then we did some transformation in this B, which is transform this f of x to exponential of negative f of x. So the minimization problem becomes the maximization problem of this exponential function. But still, this landscape is still very complicated, and it's very difficult to directly minimize or maximize it. And then in picture C, we further transformed this function by adding this quadratic regularization term here with some initial guess about this global minimizer Z. And you can see that now this landscape is much like mild, so less like complex, but still it's a non-convex function with lots of local station point, local maximizers. And in picture D, we further transformed this function by adding a scaling parameter delta, which is a small positive constant. And this delta does not need to be too small to because if it's too small and it's a denominator, it would cause numerical instability. But we do not need this delta to be too small. We just set it to be 0.25 in this example. And you can see we get this picture D, which is a very concentrated, locally concentrated landscape. And to estimate our proximal operator, as I said, it has been converted into estimate the expectation of this very simple landscape with this very simple Gibbs measure with a highly concentrated landscape. So that's the motivation. And now the question is, how do we actually compute, or how do we actually sample from this simple landscape? So there are two approaches that we considered. One is called Monte Carlo integration, which is a classical method. It's basically that you have some, say if your current iterate is like at x, then you sample a number of points under this Gaussian distribution, and then you do a weighted summation, and you get the estimation of this proximal operator. But this method works, but it usually suffers from high variance, especially when the dimensions is high, and it usually requires a large number of samples for acceptable accuracy. The new approach we propose here is called tensor-train integration. The idea is that we first construct a low-rank tensor-train or TT approximation of this function psi here, which is a transformation from the original function f. Then we just use a standard quadrature rule to estimate the proximal operator based on this TT approximation. So the benefits about this new approach is one is that it does not suffer from high variance, mainly because it exploits subjective regularity in this integrand to improve this estimation. So what is this tensor-train integration? I haven't taught you yet, and here's a short introduction. For numerical purposes, we view our function f as a high-order tensor by considering its f of psi, which are two closely related functions. And we consider a discretization of this function psi. And because we want to view it as as a tensor, right? So it needs to be restricted within a bounded domain so that we can consider mesh grid for this discretization. And a tensor chain approximation of this high-order tensor on this mesh grid Z, we call the psi dt, is given by the formula here, which is basically a linear combination, a linear summation of a number of product of a number of low-rank tensors from G1 to GD. And this G1 to GD has a name. They're called the cores. And they're basically like small third-order tensors with these dimensions. And this formula may look a bit complicated at the first sight, But you can understand this TT decomposition as simply a generalization of the standard SVD of a matrix, but generalize it to high order tensors. And the benefit of this TT approximation is that in practice, when we actually compute this tensor string approximation, we do not really like store the whole high order tensor that would cost a lot of memory. But instead, we use a randomized algorithm called TT class, and to construct a very low rank TT approximation. And by doing that, we have reduced the computational cost of numerical integration from this scale, which is exponential to dimension t, to the dimension d, to only linear dependent on its dimension d. And we did some analysis of the error bounds, and these are the results. So basically, if f is twice continuous differentiable, and if we choose our measure grid size to be this size, and we assume we have an error bound for the tensor chain approximation itself, then which is this ETT is the error between this the tensor chain decomposition and the original discretization of the original function, then we can say that the error of the tensor chain approximation of the proximal operator is bounded by this big O f delta. And if for a weaker assumption that if f is only, it's not differential, but only resides in a sublief space, then if we choose our measure grid to be this size, and ETT we assume it is below this value, then the approximation error of this proximal operator using TT integration is like a big O tilde big O of delta. So this is just that we omit some log terms with respect to delta. So basically it's saying that for a small delta, then we can get a sufficiently accurate proximal operator estimation. So now that we have the general framework, and we have Monte Carlo and tensor chain methods to estimate the proximal operator, then we combine these two things together to actually propose a practically efficient, two practically efficient adaptive IPP algorithms. So the first one is TT-IPP, which is based on the tensor chain approximation of the of this function psi. And initially, we construct this TT, which is a low-rank tensor approximation, and then we use this to estimate at each iteration. We use standard quadrature rule to get the next iterative SK plus one, and then we look at this condition here, mainly to ensure that the function value along this over these iterations are like a decrease steadily, but we also allow occasional increase. And then we, based on this condition, we adaptively update our parameters like delta k. And also, if it's necessary, we also reduce the measure size and further refine the tensor chain decomposition using this randomized TT class algorithm. And the other algorithm we consider is this MC-IPP, which is based on the Monte Carlo integration for proximal operator estimation. So because the Monte Carlo estimation suffers more from the high variance, we introduce this damping parameter alpha k here to prevent the algorithm from going along the wrong direction too far. And then we look at this condition, and we again, because of the high variance in Monte Carlo integration, we incorporate this regression step. So if we observe that function value at this y is actually higher than the past few iterates, then we reject this yk and return to this line to sample again to get a new yk that with a probability p. And then we adaptively update our value of delta and also the sample size nk. So these are our algorithms. How do these two algorithms performs in practice? And we have done a lot of experiments. Here are the results. So basically, for TT-IPP, because we need to construct a low-rank tensor approximation on a mesh grid, so we restrict our definition of a objective function within a boundary region, which is omega here. So here, it's like the range on each dimension, along each dimension is between -5 to 5. And this dimension D can be high, up to like hundreds. And then we compare our two IPP algorithms with a number of like state-of-art global optimization methods in literature. And we fix our control parameters for these two algorithms as listed in this table here. So basically, we fix these control parameters for all the experiments that I'm going to show you later, which means we do not like tune the parameters separately for each task. And then here's a table to show you the performance of TT-IPP comparing to DE's classical global optimization method, which DE is short for differential evolution, and PSO is the particle swarm optimization, and TTOPT is actually a new optimizer from 2022, which is also based on this tensor-train construction. But you can see that our TT-IPP algorithm outperforms all these different global optimization solvers on a bunch of like a benchmark a number of benchmark functions, including the grid-rank function I showed you in an early picture. And we consider the size, the dimension of this function ranging from dimension 4 to dimension 100. And we also consider other benchmark functions include in these commonly used benchmark functions for global optimization. You can see that the Bowden figure is showing that the Bowden figures are showing that TT-IPP gets the best performance on this a range of like experiments on benchmark functions. And for MC-IPP, MC-IPP because it suffers of high variance, but it also has the benefits that it's very easy to like implement, and it's not like conversion as accurately as TT-IPP, but still you can see it's comparable and in many cases outperforms other existing global optimization methods. And here are two pictures showing the convergence path of our algorithms comparing to other algorithms. So the pink curve here is the convergence path of TT-IPP, which you can see that started from this black cross, which is a random initial guess, and this pink path managed to converge to the global minimizer, which is the red cross here, in a very direct and robust manner. The blue path is for MC-IPP. You can see although it's subject to some oscillations, and but still it manages to converge to the red cross, which is the global minimizer. Whereas if we compare this with the green path on the left picture is the differential evolution, it actually does not converge to the global minimizer. Instead, it ended up at a local minimizer. And similarly for the picture on the right side, the green path is for particle swarm optimization. It also didn't converge to the global minimizer. Instead, it stuck at a local minimizer. And we also experimented on a real application in biology, which is actually the very first picture. It's a picture I showed you on my very first slide, which is the DNA chain model. So if you consider 1580 pairs on this DNA chain, then it ends up with a potential energy function V of x, which is a summation of 15 double wave functions, which could have 2 to the 15 number of local minima. And our TT-IPP and MC-IPP meant to converge to a global minimizer, and the TT-IPP actually meant to converge to that global minimizer with a high accuracy. MC-IPP is less accurate, but it outperforms all other global optimization methods that we considered. Okay, so in summary, we first proposed in the first part of the talk, we proposed a new optimizer AdaGO for deep learning. So this actually established the first theoretical framework for adaptive matrix-aware optimization, achieving both optimal theoretical convergence rates under standard assumptions and also showed improved empirical performance comparing to strong baselines Adam and Muon. And in the second part, we propose IPP algorithms for global optimization, which has theoretical convergence guaranteed under very mild assumptions, and it leverages low-rank tensor approximation and adaptive sampling for practical efficiency, and it allows it to be scalable to high dimensions. And based on these two results, there are actually a number of new, like a number of future directions. Here I mainly list like 5 of them. The first one is how to best integrate adaptivity with the matrix and the tensor structures of neural networks under common training practices. Although AdaGO has proposed a possibility that how to like best integrate, especially under less like assumptions that is weaker than standard assumptions, and when there are other common training practices such as weight decay, like normalization involved, how do we like actually propose a practically very efficient tool for large scale training? And the second direction is can we design efficient zeroth order algorithm for large scale training? So currently the Adam stochastic gradient descent, those gradient-based methods have dominated the world of large-scale training. But gradients sometimes can be annoying. Gradients can vanish or it can explode. So if we could design efficient zeroth-order algorithm, which does not require gradient information, then especially for fine-tuning, then it would be a very great result. And the third one is how to further accelerate global optimization using our IPP framework. For example, we can consider like more advanced variance reduction method, or we can incorporate the gradient information. The fourth one is that we can extend it. So currently results are on unconstrained case. We can extend it to deal with the constrained optimization problem. And the fifth one is that the recent advances in quantum computing and also in machine learning gives us the new opportunities to incorporate quantum speed up and also learn to optimize, which is to replace part of the computationally heavy component in an optimizing algorithm with a trained machine learning to further like accelerate the optimization. And here are the acknowledgement for the funding. And thank you for listening. Any questions?